Applications of forces, dynamics and inclined planes. So here we're looking at a particle on an inclined plane where the plane is rough, so there will be friction. The particle will be moving, so it's dynamic, and it's either moving with constant velocity or it will be accelerating. So here's a particle on an incline, and the force is perpendicular to the incline, so in this direction will be in equilibrium, so the resultant force in this direction will be 0. If the particle's moving down the incline or up the incline and it's moving with constant velocity, then the resultant force parallel to the incline will also be 0. Now if the resultant force is not equal to 0 in any direction, then there will be acceleration from Newton's second law, and we know everything about friction already here. Example 1. So we have this particle and it's on an incline, and this diagram is showing us that there's some friction here. Now, F equals mu r, that's the formula for friction, and we also know that there's acceleration and it's down the incline. So far we know it's a rough inclined plane because of the friction, and we know there's acceleration down the incline, so there must be a resultant force down the incline too. So to calculate the value of the acceleration, which is our first objective, we need to resolve forces parallel to the incline and perpendicular to the incline. Our first objective is to work out r. Once we have r, we can work out friction. When we have friction, we can look at forces parallel to the incline and use F equals ma to calculate the acceleration. The coefficient of friction is 0.5, and that's given. And now resolving this force perpendicular to the incline, mg cos 37, and this angle is the same as this, and parallel to the incline, mg sin 37. So resolving forces perpendicular to the incline, taking this as the positive direction, so we have these two forces. So we will have r minus mg cos 37 is equal to 0, because the resultant force in this direction is 0, there's no acceleration, everything's in equilibrium. The mass of the particle is unknown, it's m, so we will have m in our answer, and r is equal to 7.8266 times m. So we've worked out the normal reaction force in terms of m, and I'm using more significant figures here to preserve accuracy for further calculations. Now resolving forces parallel to the incline, and this is the positive direction this time, so we have this force mg sin 37, and we have the frictional force mu r. Now there will be acceleration, so there will be a resultant force this time, so F equals ma. So mg sin 37 minus mu r, so a mu is 0.5, and that was given here, times the normal reaction force, which we've just calculated, equals the mass m times acceleration. And every term has an m, so we can cancel out m throughout, so if we divide by m, and then simplifying, we have 1.98 meters per second squared to 3 significant figures. You may notice that the acceleration is a constant, it's not a function of time, so we can use Subat formulae for further problem solving perhaps. Part 2, we have to work out the displacement of the particle 2 seconds into its motion. So constant acceleration, we're going to use Subat. So this is what we're after. We need s. Initially the particle was at rest. We're not interested in the final velocity, so I've crossed out the v. We have the acceleration, and t equals 2. So Subat formula, substitute the values in, and we have our displacement, 3.97 meters. And because the particle is moving in one direction, we can look at this as the distance travelled or the displacement. They will both be the same.